Hello and welcome to this tutorial on finding the generated voltage and the efficiency in a DC generator when they are configured in series. Now, so if we configure our machine in series, we're going to have our field winding here, our armature winding, our idealized rotor, like that, and we will generate a current and a voltage. Now, DC machines, when you generate, they need to have the field excited in order to create the magnetic field that the armature is going to rotate through. And so these machines, they self-excite each other. So if you're going to configure this in series, the field winding, you want to be a very low resistance. Usually this is done with a very large diameter conductor, and you want it to be a low resistance because it is effectively acting as an impedance to the generated voltage here. So the numbers that I'm going to do in this example are slightly unrealistic insofar as the field winding is going to be a high value. The reason I'm doing it as a high value is to compare and contrast it with the other tutorial that I've done on a shunt machine, which has a higher winding. And you'll see that with the high value of field resistance, this machine is going to be horribly inefficient. We'll do it anyway. The process is the same, irrespective if we had a low field resistance, which would be more realistic, but we're going to do it with a higher one, as I said, just to provide a contrast. So the numbers that we used in the other example, we were getting an output current of 35 amps and a output voltage of 160 volts. The armature resistance was 0.2 ohms and the field resistance was 40 ohms. And as I've just said, this is an unrealistically high number for this particular example. Also, we're going to have a rotational speed here using the same of 2000 RPM, which is 208 radians a second. And we also know our basic equations of that, and torque is K phi times the armature current. So this is the knowledge that we're going to take from here. So if this is our armature resistance, our field resistance, our EA, our generated voltage, that's going to be going there. We've got a rotational speed there. We can easily see, and this is a generator, so we know that this voltage that's going to be generated here is going to be larger than this one here because we've got power flowing that way. So the generated voltage here will be the sum of the volt drops here and the generated output. So it will be RAIA plus RFIF, which is the same because it's in series. I'll call it F just for that because, plus this voltage here. So we can go through and put some numbers to this. So RA was 0.2 times 35 plus 40 times 35, and you should be seeing the problem right about now, plus our output voltage of 160. And if we go through and do that calculation there, it comes up with 1567 volts. This voltage here is significantly larger than this voltage because of the large volt drop going on across the field resistance here because of this. And as I said before, this value here is unrealistically high, but I'm doing it for this example just to compare and contrast. The process is the same, even if this is a much more realistic 0.1 of an ohm or something like that. So now we've found the back EMF, the generated voltage here, sorry. We've got the rotational speed. We can find K phi because once we know K phi, we can put it in here with our current. We can find out torque, and once we know torque and our speed, we can therefore find our powers. Because remember, the input power is the input power is the rotational speed times torque, and the output power is voltage times current, and this is what we want to know. So in order to find torque we need to find K phi, so we can multiply it by current. In order to find K phi, we're going to use these two here. So the K phi of this machine is the generated voltage over the rotational speed, which is 1567 over 208, which gives us 7.5. Huge number. Huge. So therefore, our torque, K phi times our armature current, 7.5 times 35, 263 Newton meters. This means our mechanical input power is 208 times 263, which is 54845. We're putting 54 kilowatts of mechanical energy into this thing, and we're getting out of it output power, voltage times current, 160 times 35, 5,600. We're putting 54 kilowatts in, we're getting 5.5 kilowatts out. Our efficiency for this machine configured in this way, 5600 over 54845 is 10.2%. Appalling, absolutely appalling. This is why if you're going to use a series machine to generate a voltage, you have to have a low impedance in the field. Otherwise, you can end up with this sort of result. If you've got a high impedance in your field, you might want to consider configuring your machine as a shunt machine. Make it much more efficient. Okay, thank you very much for watching this. I look forward to seeing you again soon. Thank you.